we are going to talk about power series. I know you loved it last year. All right. Good. Here we go. Do you remember that an infinite series of the form sigma, remember that just means the sum of, where your index starts at n equals 0 and goes to infinity, of an times x minus x naught to the nth power. If you go and you expand this is it expanded, right? But this is that power series right here. And do you remember what you do is you start with the index at the bottom here. You start by plugging a 0 into n. And when you plug a 0 into n, you would have a sub 0, right? X minus x naught to the power of, you're plugging in a 0 there. So this ends up going away and you're just left with a naught for the first term. And then when you plug in a 1, you'll have a1 x minus x naught to the power of 1. That's your next term. Remember, the sigma says put a plus sign in between, plugging in each of these numbers. Then you plug in a 2 in for n, and you'd have a2 x minus x naught squared. Boom, plus. And you keep going, dot, 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 until you plug in whatever is on top. In this case, it's infinity, which is the dot, dot, dot going on forever. The general term is just the nth term, an times x minus x naught to the nth power. So this is called a power series. It's centered at x naught, which is that value right there, where that will be a constant, like we usually saw, like x minus 2 to the nth power or something like that. Okay, so that's a power series centered at x naught. For a power series centered at x equals x naught, exactly one of the following is true. Either the power series converges only at that center of convergence, at that constant. So that's one possibility. There might be an interval of convergence, right? Where maybe there exists some positive real number r such that the power series converges absolutely for x minus x naught, absolute value on that is less than r, and that it'll diverge for anything greater than r, absolute value of this guy. So that's the second possibility. Third possibility is that the power series converges absolutely for all real numbers x. So big R, capital R here, is called the radius of convergence of the power series. And in this first case, when it only converges at that point, then your radius of convergence is 0. In case 3, if it converges for all real numbers, then we say that R is infinity. The radius of convergence is infinite. And then if you're in case 2, where the set of values of x for which the power series converges, it's called the interval of convergence. Well, even if we had case 3, your interval of convergence would be negative infinity to positive infinity. But in 2, you'll actually have like a number to a number. Yeah. And then, how do we find this radius of convergence? This book does it slightly different from the way we taught you in Calc BC. I'm going to keep with this way, but if it looks odd to you, come ask me during office hours. I'll explain what we did last year, but either way works. But the radius of convergence of the power series is given by r is equal to the limit as n goes to infinity of an over an plus 1. So you're not including the x minus x naught to the nth power when you're finding this r. You're only doing that coefficient with the nth coefficient, or the coefficient on the nth term divided by the coefficient on the n plus 1th term. So r is equal to this provided the limit exists, and if it ends up equaling infinity, then r is equal to infinity, and you've got that third case there. All right, so let's do some examples where we find the interval of convergence for the power series. All right, so example 1, we've got n equals 0 to infinity, n plus 1 over 2 to the n, and then x plus 3 to the nth power. And they want us to find the interval of convergence. All right, so all I care about is the coefficient. I care about the a sub n. So a sub n on this guy would be the n plus 1 over 2 to the nth power. And the n plus 1th term, or the coefficient on the n plus 1th term, would be plugging in an n plus 1 into all these guys. So it would be an n plus 1 plus 1, and then a 2 to the power of n plus 1. Well, that just gives you n plus 2 over 2 to the n plus 1. All right, so to find the interval of convergence, you need to find the radius of convergence first. So r will be the limit as n goes to infinity of, and it's an, which would be n plus 1 over 2 to the n, divided by the n plus 1th term, which is n plus 2 over 2 to the n plus 1. Well, that's ugly, right? We hate that fraction over a fraction. And so instead of dividing this, let's multiply it by the reciprocal. So we'll keep this, so it's still the limit. Don't forget your limit, because that's the whole point. The limit as n goes to infinity of the first term, I'll write as the first fraction, and then the bottom fraction I'll multiply by its reciprocal, which would be 2 to the n plus 1 over n plus 2. Like that. Okay. So hopefully you remember that. How do you get a 2 to the n plus 1? Do you remember that 2 to the n times 2 to the power of 1 is going to equal 2 to the n plus 1? Same base, keep the base, add the exponents. Right? So that means this 2 to the n and this 2 to the n over here will cancel. Yeah? And so you've got the limit as n goes to infinity of, you're left with the 2 up top and an n plus 1 and an n plus 2 on the bottom. Okay. I'm fine with you just saying you remember this, right? Do you remember when you're taking the limit as n goes to infinity? Do you see n on top is an n to the power of 1? The power on n on top is a 1. The power on the bottom on n is a 1. They have the same degree, top and bottom. And so do you remember that when you take the limit as n goes to infinity, it just ends up being the leading coefficients when the degree on top is the same as the degree on the bottom? We proved it last year by doing L'Hopital's rule. So let's do that. If you do L'Hopital's, then you end up with the derivative of this guy ends up being 2. Well, we got to remember it's the limit is n goes to infinity. The derivative on top is a 2, and the derivative on the bottom is a 1. So it's like 2 over 1, and as n goes to infinity of 2, that's just 2. Do you have to show me that work? Absolutely not, right? I mean, you're at this advanced stage, but when the degree of n on the top and the degree on n is on the bottom are the same degree, the limit ends up being your leading coefficients. So I'm fine with you jumping to that. Okay, so that's r. R is 2. So that means that this series converges for, you take this guy here, and it's just absolute value of x plus 3 is less than r. And then how we remove the absolute value on x plus 3 is you place it between the positive 2 and the negative 2. That's what it means for the absolute value of x plus 3 to be that. Remember, that's absolute value is like the distance. So the distance between x and negative 3 is 2. Is really what that's saying. And then you go and solve for x by subtracting 3 on all sides. And so x is between negative 5 and negative 1. And so your answer for the interval of convergence, we're going to write it in convergence interval notation, which would be negative 5 to negative 1. If you remember last year, we checked endpoints as well, right? We would then go and check, okay, what happens to this series at when the left endpoint is negative 5 to see, do we include that endpoint or not? And then we would check what happens to the series when x is negative 1, and we would see if we include this endpoint. And the solution manual checks the endpoints. don't check the endpoints. Don't worry about it. We're just not even going to go that far. Just give it to me with the open intervals on that. All right, let's do another example. How about if n goes from 1 to infinity of n to the nth power times x plus 5 to the nth power? All right, well, your nth term is just n to the n. And the n plus 1th term would be n plus 1 to the n plus 1 power. And so your radius of convergence will be the limit as n goes to infinity of the absolute value of the nth term over the n plus 1th term. And then you're like, what in the holy heck, right? But keep in mind that n plus 1 to the nth power times this part right here, same base, keep the base, right, is n plus 1 to the nth power times n plus 1 to the power of 1. Yeah, so I'm going to do just a little bit of manipulation here. This is the limit as n goes to infinity of, it's a n over n plus 1 to the nth power times a 1 over n plus 1. Yeah. All right. Well, this ends up being if I take this guy inside here and I divide top and bottom by n, it's another little trick we always did. And by the way, I don't need, well, whatever. Okay, I'm going to take this guy right here, divide top and bottom by n, and it will leave me with a 1 over 1 plus 1 over n to the nth power, and then times a 1 over n plus 1. Yeah. Okay. Are you ready for this trick? I don't think you'll rete, but it's going to happen anyway. All right, so now what am I left with here? I now have the limit as n goes to infinity of 1 to the power of n is just 1. And so this ends up being 1 over, but the bottom is a 1 plus 1 over n to the nth power. Yeah. I don't know if you remember this, but that denominator right there, by definition, the limit as n goes to infinity of this guy is a special number. Yeah, it's e. And so this ends up being 1 over e times the 1 over this guy, just by definition, that's how e is defined, is as the limit as n goes to infinity of 1 plus 1 over n to the nth power. And then as n goes to infinity of 1 over n plus 1, that's 0. And so it didn't even matter that this was e, right? We just got the radius of convergence is 0. So what does that mean? That means since your radius of convergence is 0, then that means that the series converges only at that x naught value, and that is at -5. It's the only part where it converges. All right. Are you expected to know the e? I'll get back to you on that. Probably not. But hopefully for some of you that looked familiar. The limit as n goes to infinity of 1 plus 1 over n to the nth power. That is the definition of what e is. So, all right, let's do another one. Oh, you get notes this time. All right, so you may need to know that. I forgot that you actually get on this test, you get cheat sheet. Okay, so let's again find the interval of convergence for this guy. So your nth term is the coefficient. So x minus 1 to the nth is, each of those guys. The an is going to be the 2 to the n over n factorial, which means that the n plus 1th term would be 2 to the n plus 1 over n plus 1 factorial. Okay, so let me do some side notes real quick. Again, before we get started, remember that 2 to the n plus 1 is 2 to the n times 2 to the 1. I'm going to use that fact. The other thing you should know is that n plus 1 factorial, truly by definition, what factorial is you start with this guy, n plus 1, and then you go times, subtract 1, that would be times n, times, subtract 1, all the way until you go down to 1, right? Multiplying it times 3, times 2, times 1. But what you usually do you remember, like when you've got 1 on top and 1 on bottom, is n plus 1 factorial really is n plus 1 times n factorial, which is, because that's what this is n factorial. So that's what we'll usually do, is you take the larger of the two factorials, n plus 1 is bigger than n, and you just expand it out until you reach on the other side of the denominator or the numerator, on the other side of the fraction bar. You expand it out until you get to the smaller of the factorials. Hopefully that sounds familiar to you. So that's how we're going to reduce this stuff. So your radius of convergence is the limit as n goes to infinity of an. And instead of writing it as this over this, I'm going to go ahead and go straight to multiplying by the reciprocal. So an would be 2n over n factorial. I'm going to multiply that by the reciprocal of the n plus 1th term, which is n plus 1 factorial over 2 to the n plus 1, like that. And of course we see now, hopefully you see that this is equal to, using my little explanation over here, if n plus 1 factorial is n plus 1 times n factorial, then you'll just be left with an n plus 1 on top. 2 to the n divided by 2 to the n plus 1, since 2 to the n plus 1 is 2 to the n times 2 to the power of 1, the 2 to the n's cancel. So you end up with n plus 1 over 2. Yeah. And the limit as n goes to infinity, that's infinity. And so when your radius of convergence is infinity, then your interval of convergence is all real numbers. And how you write that is negative infinity to infinity. And we always put soft parentheses, even if we, whatever, you never put hard brackets. But like I said before, we're not not checking endpoints this year. So, okay, we got a couple more theorems for you. There we go. All right. If f of x is this power series with an as its leading coefficient, and g of x is another power series with bn being the coefficient on each of them. Notice they both have x naught, right, as their centers, and they're both to the nth power. Those match. You're starting with n equals 0. You're starting with n equals 0, right? So the only difference is your coefficients on each of them are different. So let these guys both converge for x minus x naught less than r, right? So if they don't match in their convergence, then you're going to choose the smaller of the converter, but they need to both converge over the same interval. So then what happens is you can add or subtract them just by adding or subtracting their leading coefficient terms, the an and the bn. You can multiply by a constant, and that'll just be one of them by a constant, right? That's just the constant times that guy. That's the only thing that changed. You can multiply them together, right? Where Cn, ooh, I want to change, well, these are equal signs. I don't know why it almost looks weird. Okay, where this Cn now is a new leading coefficient, and it's equal to sigma of going from k to 0 of a sub k times b to the sub n minus k, or you'll get the same thing, this is an equal sign, of sigma from k equals 0 to n of a sub n minus k times b to the k, not b to the k, bk sub k, right? And then that is equal to, both of these ways, whichever way you choose to do it, both of them end up equaling a naught times bn plus a1 times bn minus 1 all the way through an b0. The only difference is, like, the way it's written right here is this first guy starting with k being 0 and the k is on the sub on the a. Over here you would have started with n on the a and 0 on the b, so it's just a flip-flop. But you know, when you add all these terms together, adding is commutative. So my point is, this one, if you wrote this sigma, you would be starting with this term and working your way backwards. Doing this one, you start with this first term and then work your way up until plugging in an n into k. Hopefully that makes sense. Yeah. Okay. If you take the derivative of a power series, we can do that. You just do pop and drop. Remember, you're taking it with respect to x. F prime of x is d dx of this guy. So your an's, you don't touch that, right? If you've got 2 to the nth power, you don't take the derivative of 2 to the n because you're only taking the derivative with respect to x. So keep that in mind. But it's just a pop and drop, right? You've got the a sub n, and you would have went pop that n in front and multiply it times n, and then drop the exponent by 1. So now you've got an n minus 1. Notice your index, though, now. When you take the first derivative, you're no longer up here starting with n equals 0. When you take the first derivative, you're going to start with n equals 1. If you take the second derivative, you just do the same thing. Notice index starts at n equals 2 here. You still have a sub n. We were taking the derivative with respect to x of this guy. So you still have this n. You would pop that n minus 1 in front. So n times n minus 1. And then drop the exponent by 1. So n minus 1 minus 1 will give you n minus 2. You can also find the antiderivative, right? The integral of f of x dx. And that ends up, you still have an index starting at 0. You still have the a sub n. But remember, what we would do is add 1 to the exponent. So n plus 1. But then divide by the n plus 1. And then don't forget a plus c. And all of these guys, all 1 through 6, if these two guys converge for x minus x naught is less than r, then all of these guys also converge for the same way. Okay, let's do 2 more examples, yes? And then we'll be done. All right, so example 4 says, let's find the power series expansions for f plus g and f times g if f of x is x to the n over n factorial from n equals 0 to infinity, and g of x is n times x to the n. Okay, so here your an is 1 over n factorial. Here bn is just n. All right, so you got to find the radius of convergence for each, because in order to find where they converge here, it's got to satisfy both. So let's start with the radius of convergence for f. It'll be the limit as n goes to infinity of 1 over n factorial over 1 over n plus 1 factorial, which of course is just 1 over n factorial times the reciprocal of this guy would be an n plus 1 factorial, which is n plus 1 times n factorial. So your n factorials cancel. And so as the limit as n goes to infinity of n plus 1. All right, radius of convergence. This guy converges for all real numbers. Let's find R2, find the limit. Let's find the radius of convergence of this guy, which would just be n over n plus 1. Degree on top is the same as the degree on the bottom. So this guy is just the leading coefficient would be 1. Hopefully you see that. You could do L'Hopital's. You could divide top and bottom by n. You'll have a 1 over 1 plus 1 over n. There's lots of ways of showing it. So that means this guy has an interval of convergence of, you've got x to the n. So truly it's like x minus 0 is less than 1. It's just x. So x is between -1 and 1. And so what this means, since this is all real numbers, but this one has a more limited interval of convergence, then f plus g and f times g are going to converge for this smaller interval. And so we say f plus g and f times g both converge over the interval -1 to 1. That would be the interval of convergence for f plus g and f times g. All right, how do we find f plus g? It is sigma from n equals 0 to infinity of an plus bn times x to the, well, it's x minus x naught to the nth power. And in this case, it's just an x to the n on both of them, right? So this is just from n equals 0 to infinity of an was 1 over n factorial. Bn is n, and then it's an x to the nth power. I think that looks good. And you'd have to multiply top and bottom by n factorial. Like, that's just not going to help. So we'll just stop right there. Looks good. Looking good. All right, now we're going to find f times g. F times g would be from n equals 0 to infinity. Remember, we're going to do Cn now, and then times x minus x naught to the nth power. And that's where Cn is now the sigma, this series of from k equals 0 to n of, you could choose either one. I chose a sub k, b to the b sub n minus k, like that. All right, where, what would this be? So a sub k would just be 1 over k factorial. B sub n minus k is going to be, well, let me go up here. Okay, so a sub n was 1 over n factorial. So a sub k will be 1 over k factorial. B sub n is n, so b sub n minus k will just be n minus k. So that's where I'm getting those guys. All right, so that means I've got from n equals 0 to infinity, that's this part here. Cn, though, is this guy. So it's a sigma from k equals 0 to n of ak times a sub k, which is 1 over k factorial, and then times bn minus k would be n minus k. You could have put that up top there. That would work too. So that's the Cn, and then times, we just had x to the n. And that works. We're going to stop. You'll notice on the solution manuals that some of them simplify this more. On some of them, don't worry about it. Just do that and stop. It'll be fine. All right, one more example. Example 5. We're going to write the series from n is 3 to infinity of n over n plus 1 times x to the n minus 1 in the form where n goes from n naught to infinity of an x to the n. where n naught and a n are to be determined. Sounds all complicated, but it's really not. It's a matter of this is how you change the indices and stuff. I don't know if you remember that from pre-calc or last year. Like there were times where like there were two different answers. I could have an x to the n, but then my index is different and this guy's different, right? But they're equivalent, so we're just rewriting it so that I don't want x to the n minus 1 anymore. I want x to the power of n instead. So here's what we're going to do. We're going to replace the variables. I'm going to let some other variable represent the exponent here. Yeah, and then I'll replace it back at the end. So I'm going to let k equal n minus 1, right? Because then I'll just have an x to the kth power, which is what I want here. So if k equals n minus 1, then that means that adding 1 to both sides, that n is equal to k plus 1. I just added 1 to both sides. And so in my original power series up here, everywhere I see an n, I'm going to replace it with a k plus 1. So that means I would have k plus 1 is equal to 3 to infinity. I would have a k plus 1 replacing my n up top. I would have a k plus 1 and then a plus 1 because I just replaced that n with a k plus 1. And then I've got x to the, replacing this n with k plus 1, k plus 1, and then minus 1. Yeah? And then we start simplifying. Yeah? You don't want k plus 1 equals 3 down here. No, you want k equals. So subtracting 1 from both sides, that means k will be 2. If k plus 1 is 3, then k is 2 to infinity. This is a k plus 1. That's a k plus 1 plus 1, so a k plus 2, and then an x to the kth power. There we go. We've done what we need to do. The only thing you'll do is now replace the k with the n's, just to make it the right form, because they wanted x to the n, they wanted a n, they wanted n here, so it's equivalent though. N goes to 2, and it's n plus 1 over n plus 2 x to the n. There you go. And if you, sorry about that, if you compare it, right, like compare it to these, what we're saying is these two series will produce the exact same series when you expand it out, right? It's just here you're starting with a 2. Plug in a 2, you get 3/4 times x squared. You plug a 3 in here, 3/4 x squared. You end up with the exact same series, starting, first term, second term, third term when you expand it out. So, all righty, not too shabby, right? All right. You all have a fabulous day. Bye.